Today's 310 video is all about predicting orbits, which is also known as Kepler's problem. We have two objectives. Our first objective is to explain why it's so difficult to predict the motion of a satellite in an elliptical orbit, and second, at least qualitatively, discuss how the time of flight can differ for satellites in elliptical orbits depending on the region of the orbit that the satellite is traveling in. And this discussion is only going to be high level, and so I'm not going to give you a lot of the details of how we go about solving these problems. I'm merely going to motivate the importance of why it is that we care to work through these problems. So to begin with, let's think back to our space history lesson and think about Kepler's second law. So Kepler, one of our early space explorers, in his second law stated that the line between an orbiting planet and the sun sweeps out equal areas in equal times. And the net effect of this is that our satellite, as it's traveling around the Earth, or as Kepler saw, a planet as it's orbiting the sun, is going to be moving slowest out here at apogee. So it's going to sweep out an equal area in equal time, and it's going to be moving very quickly as it is over here near perigee. And so what that means for us is that our satellite in an elliptical orbit is not going to be moving at a constant velocity. But for ease of use here, let's consider a circular orbit to begin with. So for a satellite in a circular orbit, its velocity is actually going to be constant. Since it's sweeping out equal areas in equal time, if I was to take an equal chunk, an equal pizza slice of this orbit here, it's going to be an equal area in equal time. And so to figure out where the satellite is at a future position, I simply can take the ratio of the satellite's period. And as a reminder, to calculate our satellite's velocity, it's going to be equal to the square root of mu over r, where velocity is our satellite's speed and our r is our satellite's position in terms of magnitude. So for an elliptical orbit, our speed is not, however, constant. And so that means that it's going to be a lot more difficult for us to actually predict where exactly the satellite is going to be. The velocity equation for a satellite in an elliptical orbit is this: v equals the square root of 2 times the quantity mu over r plus our specific mechanical energy, or epsilon. So here it's a little bit more difficult for us to predict where our satellite's going to be at a future time. And if I give you an initial position, a final position, it is somewhat challenging to figure out where my satellite is going to be. And so we're going to work through the details of how we actually solve these problems in class. But the reason we have to go about solving this problem using Kepler's method instead of a simple ratio related to the period is because our satellite is not moving at a constant speed on an elliptical orbit. So here's some more vocabulary that you're going to use in class, and so I wanted to introduce that to you now. Our first is the mean motion, which is used here as the variable n, and it's the average speed that the spacecraft is actually moving at in terms of radians per second. So it's kind of our average velocity. So our satellite might not be in a circular orbit. Oftentimes will be in an elliptical orbit, but it is going to have some mean motion, and so this n becomes the average value of that. You'll find the equation for that on your equation sheet. And we also have the time of flight, which is often abbreviated TOF. That's the time it takes to go between two positions on an orbit, and it's often given in seconds. Then we have something called a mean anomaly. So just as we were discussing before with our classical orbital elements, the true anomaly is our spacecraft's position with respect to perigee. So that's down here at the bottom. True anomaly is new, spacecraft position with respect to perigee. We're going to have what we call a mean anomaly. So it's going to relate the motion of our spacecraft to the circular motion on an ellipse. So we're going to talk more about what this actually looks like in class, but for right now, understand that a mean anomaly is relating the motion of our spacecraft to the motion of a circle on an ellipse. So the eccentric anomaly, rather, is E, and that's mathematically related to M. So we're going to have these three different angles. We're going to call them brothers later, so they're the anomaly brothers. There's the true anomaly, the eccentric anomaly, and the mean anomaly. And they're all going to be related, and we're going to use them all to figure out where our spacecraft is either at a future time, or given 2 times, how long it took our spacecraft to get there. So hopefully through even just this brief lesson here, you've learned why it is that it's necessary to use Kepler's equation here and Kepler's problem to solve for our future position on an elliptical orbit. We've talked about our spacecraft's motion on a circular orbit versus an elliptical orbit and how it's not moving at a constant velocity in an elliptical orbit. And we've at least briefly introduced the 2 versions of the problem that you're going to see. So the first is to find the time of flight between 2 known orbital positions, and the second is find a future position given a known time of flight. Thanks. That's it for today. We'll see you. All right, guys, here's the relationship between true anomaly, eccentric anomaly, and mean anomaly. This animation is shown in the Anomaly Brothers spreadsheet that you can open up and run on your own. But essentially, our satellite's traveling here on an elliptical orbit, and its position is going to be described from perigee in terms of this angle nu. And then we also have this eccentric anomaly, which is a circle. But this circle is essentially the same width as the major axis of our ellipse. And then we have our third anomaly, which is our mean anomaly, which is shown here in yellow, which is essentially a circle that is centered there at the Earth. And what you'll notice is as I animate this, and as our satellite moves around this, essentially the elliptical orbit, its speed is not constant. It kind of whips right around here by perigee, and then kind of slows down as it gets out here to apogee. And the eccentric anomaly, the red angle, is also kind of both accelerating around perigee and also slowing down around apogee. But this yellow angle, the mean anomaly, is actually staying constant. And so that's kind of the relationship that we end up exploiting with Kepler's equation so that we can kind of relate these three things. One other thing to notice how all these angles look very similar as we approach perigee. And then once we get to perigee, they're all zero, so they all equal each other, which is 0. And then once we get over here all the way out to apogee, again we have a similar situation. They all start to kind of converge to close to the same angle the closer we get to apogee, and here they're all equal to 180 degrees or pi if we're talking about radians. Alright, so that's the Anomaly Brothers.
Oh yeah, you know who it is. It's Major Cunningham from the Astro Department. Let's do another video. Boom! Alright, what we're going to be talking about today is how you mathematically chunk through the process of predicting where a satellite is going to be in a given amount of time. That's one situation. And how long it might take a satellite to get between two given locations. And so those are kind of the two main situations that we find ourselves in the business in any event, is that, well, maybe I got a good read on something's location, but it's in an elliptical orbit. As you guys might remember, it's tough. It's actually really tough to predict where something is going to be in an elliptical orbit. Why? Well, because on the equation sheet, you guys might remember this equation here. Now, if you have a circular orbit, that's kind of an easy kill because its speed is, we assume in Astro 310, and it's mostly true, that it's constant, right? So really it just becomes a matter of hacking your watch and then seeing how big the orbit is and just waiting for it to come around the next time. Not so with elliptical orbits, because now you have this equation that you guys remember. Look, so at this point, it depends on how far, with an elliptical orbit, it depends on how far away you are from the Earth at any given moment, how fast it's going. So the prediction problem becomes so much more complex. And Johannes Kepler, who has been basically running our class so far as mathematics go, came up with the best solution that we have so far, right? 400 years ago, and we haven't come up with a better solution yet than his mathematical prediction process of orbit prediction. And you might say, well, how on earth? Like everything else has advanced in the last 400 years quite a bit. Well, we still haven't quite mastered how to do a restricted 3-body problem, let alone more bodies than that. And so we are still left with, we have really good approximations for where things will be in orbit. We have really good tools to approximate where things will be in orbit, but they're compute intensive. And in fact, what I'm going to show you today, you can imagine the orders of magnitude difference in predicting, in the difficulty, I would say, of predicting something in an elliptical orbit versus a circular orbit. So without further ado, let's go ahead and jump into one of these problems. Okay. So what I did is I have the homework problem from the homework problem set from last year, and they're really good because they don't let you take any shortcuts. So I sought these out specifically because it shows you the whole process, and this hopefully will be a good, as always, a good resource for you to come back to. So it says the following. It says the satellite is an elliptical orbit with the following COEs. Okay, so major axis of 18,500 kilometers, eccentricity of 0.2, inclination of 60, RAN of 0, omega of 90, and a true anomaly of 270. And it says, okay, if I give you that, how long will it take the satellite to travel from its current position at the ascending node, which it says here is true anomaly of 270, to the descending node? So it's actually going to cross over perigee, and that's going to be something valid later. So this really becomes our true anomaly final here. So here's how I like to do these. And again, there's multiple ways to skin this cat. I am just showing you my way. Housekeeping steps. First things first. I want all my values to be in radians. And so first things first, inclination, it's a red herring, does not do anything for us in these problems. Ran, red herring, doesn't do anything for us in these problems. Argument of perigee doesn't do anything for us in these problems. So really I'm left with my true anomaly initial, my true anomaly final, A and E, that really actually matter. So anything that's an angle in these problems, put in radians. Cannot foot stomp it enough. What do I mean by that? Well, okay, so true anomaly initial, they gave us as 270. That's degrees, man. I want to convert that to radians. So in every 180 degrees, there are pi radians. So let's see what that gives us on the old trusty calculator here. That spits out 4.7124. And I'm going to carry four digits here after the decimal. That's going to come in handy because if you truncate your decimals too early with these orbit prediction problems, you end up carrying pretty significant rounding errors that will foul up your answer. So carry at least 4 for now. Okay, great. Let's do the same thing, sorry, with true anomaly final, which they gave us to be 90 degrees. Let's convert that bad boy into radians. .5708 radians, remember. Okay, good. That's our first housekeeping step. All right, now let's step back and try and think about what's actually happening here. If I start off at 270, that is a position in the orbit where I'm just about to hit perigee, right? I've almost completed an orbit. And it says my true anomaly final in this situation is 90. So that means in this example, well, my satellite has essentially done, it started off down here at true anomaly of 270, right, which is 4.7124 radians. And through the course of this problem, it swung past perigee, which is right here, right, and then the problem says, okay, I don't care about after this. I just want you to tell me how long it took to get to true anomaly final of 90 degrees. Picture helps me just because this fact that it has swung through perigee in the course of the problem, that fact matters. Fact matters, and we're going to talk about it a little bit later. Okay, now we've done our housekeeping steps. Let's take a step back and think about what we're actually trying to do here. We're given a true anomaly initial. We're given a true anomaly final. We would like to get time of flight. The problem says, how long will it take? So when you say, how long will it take, that means it's looking for time of flight. Okay. The way we do this is we use our true anomaly initial value to get eccentric anomaly initial. We use that to get a mean anomaly initial. And we're going to plug that part into the time of flight equation. We're going to do the same thing with true anomaly final. We're going to use that to get eccentric anomaly final. We're going to use that in turn to get mean anomaly final. And we'll plug that in the time of flight equation, and that, like magic, will give us our time of flight. Cool. All right, well, let's begin. So, true anomaly initial. Where we are in the equation sheet is at the upper right side of the front page under orbit prediction. It's got everything you could possibly want. So I want to find eccentric anomaly initial. Well, it says my equation for this is actually bounded by cosine of the eccentric anomaly initial equals eccentricity plus the cosine of true anomaly initial over 1 plus eccentricity times the cosine of true anomaly initial. Okay. I'm just going to write it again because it's so important. Remember radians. Okay. He's very happy. I remember radians. Okay. So let's do some plug and then also some chug. 0.2 plus cosine of true anomaly initial in radians, which we found was this 4.7124 all over 1 plus 0.2 times cosine 4.7124. Boom. Okay. Now let's do some plug and check. Now, everyone has a different calculator. Even if you're using the honor later, there's a function in your calculator that allows you to switch modes. I got to switch from degree mode over to radians mode. I wonder if you can see that. Ah, there we go. See how it's in degrees? My calculator is almost always in degrees. With these problems, you just got to switch it over to radians. Okay, now comes the plug and also the chug. Alrighty. So that gives us almost exactly 0.2. As in, I get 2000. Great, but eccentric anomaly initial is the inverse cosine of that, right? I still have to take care of this cosine part. Let's see what it gives us. Alrighty. Gives us 1.369 radians. Okay, so these equations are tricky, and the reason I want to tell you that they're tricky is because let me jump over to the Excel sheet. This demo is just priceless. It's so helpful. So on this demo, as you can see, as I swing through, perigee, and then I come up over to apogee, and then I'm swinging past apogee around towards perigee. That's where our problem begins, right? That's where our story starts, if you will. So at that point, we have kind of crossed from this upper area, which is between 0 and pi, down to this second part of the orbit, which has a true anomaly of between pi and 2 pi. So what I mean is, if our true anomaly initial is between if it's between pi and 2 pi, which it is, right? So let's kind of step back here for a second. Pi is 3.14. 2 pi is about 6.28. Really rough, but stick with me. If true anomaly initial, which our true anomaly initial is 4.7124 radians, does that fall between 3-ish and 6-ish? Yes, it does. So let's hop back over to the Excel sheet. That means if your true anomaly initial is in that bottom half plane, that's what we call it a half plane, or it's basically half potato, half ellipse, right? If it's in the bottom half ellipse, that means that eccentric anomaly initial and mean anomaly initial also have to be. So we have to do, you guys might remember a similar process from when we were calculating COEs, right? We had this quadrant check that we had to do, and we had to do some manipulation to our final answer to get it to be the correct final answer, because the equation is being silly and spitting out something that's in the wrong half plane. So what I'm trying to say is how this manifests is 1.3694 is what we got spat out for eccentric anomaly initial. I appreciate you, calculator, but you have failed. You're drunk, go home. No, it hasn't failed. It's given us the answer in the upper half plane, but we know that our true anomaly initial is in the lower half plane. So what I have to do is I have to take 2 pi minus my answer for eccentric anomaly initial to get the correct eccentric anomaly initial. And this gives us 4.9138 radians. Ah, much better, right? That checks. That checks. Because 4.9138 is between pi and 2 pi. It is between 3-ish and 6-ish. That's what eccentric anomaly should have given us the first time. Okay, it's that manual half plane check process. This is where you make some money here. Half plane check. You have to do that for eccentric anomaly initial. Okay, I'm going to switch over to graph paper now, because I'm running out of space. The size that I write at with my penmanship, I need extra sheets of paper. Okay, let's get this over here. All right. Next step. This is all true, but I had just written that from a previous problem. So you know what? Let's start off with a clean sheet of paper here. All right, we found our eccentric anomaly initial. And as you guys recall from the process, now we are going to plug that into mean anomaly initial. My little pinky finger right there. Okay. Mean anomaly initial. Give me an equation sheet. This one right here looks like it would be helpful, and it is. Okay, this is really a great matter of just plug and chug. What did we get for our eccentric anomaly initial after all was said and done? We got 4.9138 radians. So let's plug that in. I probably don't need to write the word radians there. Now let's plug and chug and see what comes out for mean anomaly initial. Remembering that it's likely that we'll have to do a half plane check here, but one crisis at a time, right? Right there. Oh, no, that came out all right. So 5.1097 radians is what I got for my mean anomaly initial. Ask yourself, is that between 3-ish and 6-ish? Yes, it is, right? Smack dab in the middle is 5-ish. So no half plane check needed. Or rather, we did the half plane check and no subtraction is needed. Check. Okay, well, this is going to come in handy in a second. We need to now run the same process. If I were to kind of give these checklist step names, I would say my housekeeping step is step 1, then going true anomaly initial all the way to time of flight is step 2, and going mean anomaly initial up to time of flight, or sorry, true anomaly final, blah, blah, up to time of flight is step 3. So great. All right, so over here with our step 3, we're going to kind of repeat the same process, which is nice. So true anomaly final, we remember was 90 degrees, but I don't like degrees, not for these problems. 1.5708 radians is what I got for radians. Going back to our equation sheet, let's use the same equation again. Eccentric anomaly final, right? I'm going to isolate the eccentric anomaly final here by taking inverse cosine of both sides. E plus eccentricity, rather, cosine of true anomaly final over 1 plus eccentricity cosine of true anomaly final. Let's plug and chug. Let's see here. 0.2 plus cosine of 1.5708 over 1 plus 1.2 cosine 1.5708. What's this going to give us? And remember, we're going to have to do a half plane check. Always got to check ourselves before we wreck ourselves. Okay, oh man, that gives us just about exactly 0.2 radians as well, until we take the inverse cosine of it, and that spits out 1.3694 radians. Okay, so let's ask ourselves, let's do the half plane check. True anomaly initial, or sorry, true anomaly final. All right, we've swung up here past perigee once. True anomaly final is 90 degrees, which we found was 1.5708. Is 1.5708 between 3-ish and 6-ish? No, but that's okay. Why? Now, let's make an addendum to our drawing to kind of see why. True anomaly of 0 is perigee. You guys buy that. True anomaly of 180, or pi, is apogee. We'll make a little thing for apogee here. What I'm trying to say is true anomaly initial is in this upper quadrant between 0 and pi, because 1.5 is between 0 and 3-ish. That means that eccentric anomaly final and mean anomaly final also have to be between 0 and 3-ish, right? So our half plane check is just making sure that true anomaly initial is in the same half plane as mean anomaly initial and eccentric anomaly initial. Same for final. True anomaly final happens to be in this upper half plane. So that's just going to be between 0 and pi. So that means that its brothers, true anomaly final, and its brothers, eccentric anomaly final, mean anomaly final, also have to be in the upper half plane. Well, let's come back over here. We got our eccentric anomaly final to be 1.3694. Is that between 0 and 3-ish? Yes, it is. So it passes our half plane check. All right, so we're good to use then the mean anomaly equation. Bring this back over here. Mean anomaly equation, which is right her eccentric anomaly final minus eccentricity sine of eccentric anomaly final. Okay, great. Plug and chug becomes 1.3694 minus 0.2 sine 1.3694. And when we have plugged and also chugged, that is going to give us 1.1735 radians. Okay, let's check ourselves again. Is that between 0 and 3-ish, right? 0 and pi. Yes, it is, right? So our half plane checks have checked. We're good to go. We are now finally at the point. Finally at the point. Last step. We can calculate time of flight. We have all of the ingredients that we need. So here's the equation that I am going to use. Mean anomaly final. Do we have that? Yes, we do. Minus mean anomaly initial. Do we have that? Yes, we do. Equals n, which we haven't solved for yet. We'll solve for it right now. Time of flight minus 2 pi, I'm going to write it slightly differently, times this value k. K is going to end up being the number of times the satellite has swung through perigee. This is why our initial picture was so important, because just by working it out, we found that it has swung through perigee once. That means our k is going to be equal to 1. So let's begin our plugging and chugging here in a second. First thing I need to do is actually solve for n. Well, our equation sheet has n for us. It says it's the square root of mu over a cubed. We haven't used sine major axis up to now, but we're going to use it now. N is mean motion. N for mean motion. This letter makes sense. No, I kid. It does not make sense, but N stands for mean motion. And when we do some plugging and chugging, we remember that our sine major axis given to us was 18,500 cubed. Let's see what that gives us, eh? cubed. And if your spidey senses are tingling because it's a super tiny number, not to worry, it's supposed to be really tiny because it's in radians per second. And satellites don't cover that many radians in a second. They cover degrees in a second, but when we convert it to radians, it ends up being really tiny. So that's okay. Just saying, you know, like I get times 10 to the negative 8th. Oops, no, I don't. Oh, this is good. This is good that you saw me do this. I got a small number, which is okay, but I forgot to take the square root. Yeah, so partial credit for me. Remember to take the square root. Kind of glad I did that because that's a common error. So common that I did it, but still small. 2.5091 times 10 to the negative 4th radians per second. That's n. All right, now it's time to plug and chug. Of course, first of all, what I like to do is solve algebraically. You know me. I am an algebraic kind of a guy, so I want to isolate time of flight. What I'm going to do here is mean only final. That's mean only initial. I'm going to take this term, add 2 pi k to both sides. Equals n times time of flight. That means to get time of flight on its own, I'll divide both sides by n. And I can do that because that is allowed. And we remember we said that the number of times satellites swung through perigee, this is this k value. And from our picture, we found that k was 1 because look, it's like bonk, swung through perigee once. So I'll go ahead and throw a 1 in there. We're in. Now we're finally ready to plug and chug. Let's do this. Mean anomaly final we got was 1.1735 radians minus mean anomaly initial, which all the way back up here was 5.1097. You might say, oh shoot, we're about to get something negative. Well, that's where that 2 pi came in handy, right? The number of times it swung through perigee. We're going to go ahead and add that 2 pi here, and that'll fix the negativeness that this number would have had if we hadn't have done that. If we hadn't done that. Okay. It's time for the final plug. Let us do it. I'm really encouraged because that gives us something sane. Gives us 9354.036. Since this is the final answer, I'll go ahead and truncate the 3 digits here at the end, 6 sig figs. Time of flight comes out in seconds. For sanity's sake, now you don't have to do this. This is where this ends, right? 9,300-ish seconds. Just as a sanity check for myself, I divide by 3,600 and I put that into hours just because that's how I think of it. So if I divide by 3,600 here, just for fun, right? The problem doesn't say to do that. 5, 9, 8-ish hours. Yep, that makes sense. LEO orbits, right? Orbits that are down around, between 100-ish and 1,000-ish kilometers generally have periods between like an hour and a half to 2 hours. And this one has a semi-major axis of bigger than that. So we should expect it to be bigger than the normal, 90-minute, hour and a half orbit. So yeah, this is great. Okay, that's situation number 1, where you are given a true anomaly initial, true anomaly final, and asked to find time of flight. Remember, we did our housekeeping. We put everything in radians, first things first. And then the other thing that we remembered is to always see when we're working for true anomaly initial all the way across to mean anomaly initial, we want them all to be in the same half plane, and the same for true anomaly final. And boom, we found our time of flight. Nicely done. Alrighty, you guys, let's do a problem that is kind of like the sequel to the previous problem we did, but more correctly, I guess it would be just the other the other form, its final form, if you want to call it that way. This one involves what we call numerical iteration. It's just going to be a hoot, but it's actually a little bit simpler in its own way. So anyway, enough prognosticating from me. Let's get going. All right. So the problem says this. It says the satellite from problem 1 is now at perigee of its orbit. Where will it be in 12 hours? Okay. First things first. What have we been given here? Heyo, given a time of flight. We're going to have to convert that to seconds. So let's multiply by 3,600 seconds per hour. That'll give us a time of flight of, we need it in seconds, right? That's how it'll be able to be calculated. 43,200 seconds. Okay, great. Now, true anomaly initial, it says, is perigee. So let's draw our little picture as always. Oh man. Worst ellipse I've drawn so far. Okay, it says I'm right out here. You know what? I'm actually just going to try and do it a little better. Excellence in all my potatoes. Excellence in all my... Oh, there we go. Geez, that's so much better. All right, so there's Earth. It says that the satellite, oh, it's a little bit better, is here at perigee for the problem starting off. So it's 0 degrees. Okay, remember, for our housekeeping step, we're going to do the same thing as the previous problem. As far as I want my true anomaly initial in radians. Well, 0 is 0, right? Even if I multiply by our conversion factor, it's also 0 radians. Now, I want to show you a trick and then prove that it's right. So here's what I'm going to do. Here's the trick. Hooray! If your true anomaly initial is 0, that means that your eccentric anomaly initial and mean anomaly initial are also 0. Why is that? Okay, well, let's jump over to our Excel sheet. So I'm just going to swing around our lines here a little bit. There they go. Oh, they're swinging past perigee. And then here it is swinging past apogee. Let's swing back over to perigee again. So as you guys saw, at perigee and apogee, those 3 lines are all overlapped on top of each other. Well, what is perigee? Perigee is 0 radians. So that means if the satellite's at perigee, it basically chains eccentric anomaly initial and mean anomaly initial to also be 0. Same thing. Let's run it over all the way to apogee. The lines are lined up on apogee 2. That means that eccentric anomaly initial and mean anomaly initial are chained to pi, right? If true anomaly is pi. So let me finish writing out that rule. True anomaly final. Oops, sorry. Actually, shouldn't even use an initial here because really it just means this could be true for final or initial. Basically, if true anomaly is 0, that means the eccentric anomaly and mean anomaly for that time are also 0. For same thing for pi. That's what I was trying to get at. That means that eccentric anomaly and mean anomaly are also pi. Of course, out of habit, I put degrees there. Shouldn't have done. Okay, so if true anomaly is 0, that means that basically chains eccentric anomaly and mean anomaly to also be 0. If your true anomaly is pi, E and M have to follow it and also be pi. Yeah, so here you can see as we swing around from perigee out to apogee, all of the 3 brothers, if you will, the true anomaly, eccentric anomaly, and mean anomaly are all in that upper half plane. And then as soon as we pass apogee, well, first let's look at apogee. At apogee, all three brothers are stacked on top, right? They're all the same value at pi. And then as they swing past apogee, the three brothers, true anomaly, eccentric anomaly, and mean anomaly, are all in the lower half plane. So this is why if you're, for example, your true anomaly initial is up in that upper half plane, and then true anomaly, I'm sorry, if true anomaly initial is up in the upper half plane and eccentric anomaly, the equation tells you it's in the bottom plane, can't be, right? All these lines are always in the same half plane. So that's what this little demo is meant to show you. Okay. So I don't want you to take that for granted. I want to prove it. So let's see here. Let's use our cosine of eccentric anomaly initial. Let's find it. Let's prove ourselves this trick really works. Okay, so remembering that I get this from my equation sheet, right? The cosine of eccentric anomaly is that gobbledygook. Well, let's see. Actually, let me not put an equal sign here. Let's go ahead and take our eccentric anomaly initial and isolate it. Let's see here. 1 plus e cosine initial. Okay. Inverse cosine. Oh, we're going to have to get a little bit tiny over here. ER eccentricity is still 0.2 plus cosine of, remember, our true anomaly initial is 0. Cosine of 0 over 1 plus 0.2 cosine of 0. Okay, so what does this come out to be? Inverse cosine of 0.2 plus 1. Do you guys buy that the cosine of 0 is 1? Plus 1 plus 0.2 cosine. Oh, well, cosine of 0. I'm just going to go ahead and replace it with 1. So what does this be? End up being, I should say. It ends up being 1.2 over 1.2 equals the inverse cosine of 1. In case you're curious, that works out to 0. Okay, so that means our eccentric anomaly initial is 0. Just like the trick said, so it must be right. Well, let's see if it works for mean anomaly initial too. I'm going to grab that right off my equation sheet here. Mean anomaly is eccentric anomaly initial minus e sine eccentric anomaly initial. That means 0 minus 0.2 sine of 0. What's the sine of 0? 0. This means this is 0.2 times 0. 0 minus 0 will all be. The trick works like magic. So what I'm trying to tell you is on a GR, if you're trying to save time, make sure to check if true anomaly initial is 0 or pi, because that will chain eccentric anomaly initial, mean anomaly initial to also be either 0 or pi, respectively. And you don't have to go through this process. You can trust the rule. We just proved it. QED, right? Thus, it is proven. So in our case, we proved to ourselves the trick works. Okay. Well, that's great and all, Major Cunningham, but what's the overall process for this problem here? Well, we're going to take true anomaly initial. Oops. And you might remember the kind of little chain process I drew here. We use true anomaly initial to get eccentric anomaly initial, then mean anomaly initial. We used that to get our time of flight because we did true anomaly final, right, from before. But instead of two basically ingredients going into time of flight, we have time of flight, and we're just going to keep walking it back to get our mean anomaly final our eccentric anomaly final and our true anomaly final. Because really it says where will it be in a certain amount of time. It's asking for where will it be. Means it's asking for true anomaly final. Okay. So let me come back to this because we just proved that if true anomaly initial is 0 or pi, right? If it's 0, then that means E and M are also going to be 0. And if it's pi, they're also going to be pi. But the problem gave us true anomaly initial of 0. Great. That means we did this step. True anomaly initial was given. Because it's 0, that means E sub I is 0. And mean anomaly initial, M sub I, is 0. All right, now let's plug that in the time of flight. So if I was going to kind of put some steps on this, you're going to do this process here. Step 2 is going to be to find time of flight. And then step 3 is going to be to go through this process. Bingo, bango, bongo. Okay, so we've done step 1. That was all this. Now let's do step 2. Let's get that time of flight. What say you? I say yes. Okay, we're going to just drag our true anomaly, our time of flight equation off the equation sheet. Anomaly final. Let's see. I should amend my step. Actually, what I want to say is that step 2 here is using time of flight to get mean anomaly final. So I don't want to make this too much of a checklist-based process, but these are kind of recipes. So using time of flight to get mean anomaly final. That's step 2. Okay. Anyway, so mean anomaly final. Let's drag it off the equation sheet. Minus mean anomaly initial. I'm using this one right here for you guys following along at home. Is mean anomaly, mean motion times time of flight minus this pesky 2 pi k thing. We're actually going to use it in a different way this time around. It's kind of cool. So let's plug and chug as much as we can. So first things first, we're going to have to do the process of finding what mean motion is. It's mu over a cubed. We're just using that same equation as before from the equation sheet. Let's plug and chug. Percent major axis is still 18.5. So that's convenient. So I guess I could take the mean motion from the previous problem and not recalculate, but I'm just going to recalculate. Square root of that bad boy. 2.5091 times 10 to the negative 4th radians per second. Okay, great. Here's what I'm going to do. I'm going to leave this 2k pi thing alone for a second. And this is where you really start to see some of the fudge factor and the imprecision of this process. Kepler gave us our best approximation, right? We're using 2 circles interlaced to try and find out what's going on with an ellipse. That doesn't mean it's perfect. It doesn't mean it follows the same very linear, perfect mathematical processes as before. Like, would I ever tell you to randomly leave out a variable in any of these other equations in the equation sheet? No, I wouldn't. But for this, we are trying to find where the satellite's going to be in a certain amount of hours, which is a very real-world practical problem. I'm going to have to use some fudge factor. So anyway, step 2.1, if you want to call it that, leave that alone for now. And just find mean anomaly final, like this. We'll plug and chug, and we'll use 2 pi k in a second. Let's plug. We found that mean anomaly initial was 0 from before. And now let's multiply 2.05091 times 10 to the negative 4th. Times our time of flight in seconds. That's why I converted it in seconds up here. That's in radians per second, and that's in seconds. Okay. Okay. Awesome. This gives us and some amount of radians. It gives us 10.8391. Again, carrying all those digits. Radians. Let's think back to the previous problem. If you remember, I had drawn you my elliptical orbit with Earth right here-ish. And we have to do this half plane check thing. If you remember, if we divide the orbit in half like this, you know, your true anomaly initial, try to make that a little more of a dotted line. Yeah, okay. True anomaly would be 0 right here. True anomaly would be pi over here at apogee. So remember, if I get true anomaly initial to be in the upper quadrant, I want it to be in that upper quadrant for E and M. Same thing if it's in the bottom quadrant. So I'm trying to do my art class shading in a different direction here. That's why computers exist, so I don't have to draw. But not a bad thing. Anyway, so remember, yeah, if true anomaly initial is between 0 and pi, that means its friends E and M have to also be in this upper quadrant between 0 and pi. Same thing if it's, you know, between pi and 2 pi. But here's something interesting. A full orbit worth is 2 pi of true anomaly. What is 2 pi? 2 pi is about 6.28ish, right? So are you telling me that this mean anomaly final is spitting out something that's more than 1 orbit's worth of true anomaly, basically, or sorry, of rotation, I should say? Because 2 pi of rotation for true anomaly, for eccentric anomaly, and mean anomaly is still 1 orbit's worth. And this sucker, this mean anomaly final, how dare it, it gave us 10 point something something. So that's far more than just 1 orbit's worth of rotation. That doesn't do us much good. What we have to do is get this number. This is another kind of a fudge factor thing. I have to get this number under 6.28 because I'm really just concerned about 1 orbit's worth of rotation or less than 1 orbit's worth of rotation. So I'm going to subtract 2 pi's from this number until I get under 2 pi. And if that makes your head hurt, not to worry. It's a little bit of a mind game. So I'm just going to say 2 pi so I don't carry a rounding error. And then you can just plug that direct into your calculator. This gives us 4.55596. 55596 radians. We have example problems where mean anomaly final spits out something that's almost like 30 radians. So you have to keep subtracting 2 pi and keep subtracting 2 pi until you get under 2 pi. I know it's kind of weird, but you want the final number to be between 0 and 2 pi because that's just 1 orbit's worth of rotation. The mean anomaly final equation is very eager to serve you. It's very happy, and it says, you want to know about the rotation? I'm going to give you all the rotations. I'm going to give you all the rotations this thing's ever done in the course of the problem. And you're like, okay, chill, mean anomaly final. I appreciate you doing that, but I'm only really interested in 1 orbit's worth of rotation. And it's like, oh, okay, well, I guess you'll have to subtract 2 pi's from me until I finally get under 2 pi worth of rotation. You're like, okay, I kind of wish you would be a little more chill, mean anomaly final, but that's just how you are. Very eager little variable. Okay. All right, all joking aside, we only had to subtract 2 pi, 1 iteration, 1k, right? 1 pi, 2 pi rotation off of mean anomaly final to get under 2 pi because 4.5596 is between 0 and 2 pi, which is 6.28. Excelente. Let's go to a new sheet of paper. Actually, I'll put this over here. Alrighty. So now let's go back to our little process. We've gone all the way through using time of flight to get mean anomaly final. This is where we're going to have to do this thing called iteration. We're now at step 3 using mean anomaly final to get eccentric anomaly final. Okay. Let me put that up there from right meow. So now we're on step 3. I want to get eccentric anomaly final so that I can eventually get true anomaly final, right? And that's the holy grail of this problem. I want to get true anomaly final. So eccentric anomaly final is a step on that process. So I'm going to use and then manipulate this equation right here, m equals e minus e sine e, little e, sine big E. But I'm going to switch it around like so. I'm going to try and isolate eccentric anomaly final. But you're going to find this kind of to be an interesting issue here, because I can get eccentric anomaly final on its own, but I can't get it out of this E sine big E equation. Okay, one crisis at a time. Let's see. Mean anomaly final. I rearranged the equation as much as I could. Do you guys understand or buy the fact that I'm telling you that I can't get eccentric anomaly final on its own out of this sine? Because if I were to try and get rid of this sine function, I'd have to take inverse sine of everything else, and that's fine. That would give me eccentric anomaly final on its own over here. But then I'd have inverse sine of eccentric anomaly final over here. This equation is what we call transcendental in eccentric anomaly final. So transcendental in the variable of E sub f. Means you can't get it alone. Cannot find a way to get it alone. That's okay. We've got a solution for that. So first thing you're going to do, you're going to use mean anomaly final right here, and also use mean anomaly final as your first guess for eccentric anomaly final. Here's how this is going to work out. From before, we found that our mean anomaly final was this long 4.55596. So for our first guess, or first try, if you want to put it like that, eccentric anomaly final is this mean anomaly final plus E sine mean anomaly final, right? It's our first guess. So what's that going to look like numbers-wise? Well, it's going to look like this. 5, 5, 5, 9, 6 plus eccentricity, which is 0.2, times the sine of our guess, which is 4.55596. Well, what does that spit out? Let us see. Huh. Gives us 4.3. 5, 8, 4. Okay. That's fine. Let's do our second try, because we're not there yet. I'm going to show you why. Okay, so I'm going to label EF1 as our first try. EF2, our second try, is going to be mean anomaly final. And here's where it gets a little weird, plus E sine, not original mean anomaly final. We're going to use E sine of what we got for the previous problem, or for the previous iteration of E. What's that going to give us? Let's see, 4.55596 plus 0.2, fine, of what we got from the previous. Ooh, that gives us 4.3684. You might say, okay, can you just stop for a second, Major Cunningham? Why did you go past this first iteration of eccentric anomaly final? I'll tell you why. We want our answer for eccentric anomaly final to converge. This term converge means stop changing significantly. Stop changing much. How much? How much is enough? We decide. Right? We the space operators decide. We the engineers decide. In Astro 310, use a convergence criteria of 0.0001. What on earth is a convergence criteria? Okay. What that's talking about is how precisely do you want your eccentric anomaly final to be? And generally, in Astro 310, unless you're told otherwise, notice how the problem doesn't give us convergence criteria at all. It says, up to you, buddy. Well, it's not really up to you. Use 0.0001. So what that means is I want the tenths, hundredths, thousandths, 10,000th place to stop changing. Okay? And or let me put it this way. All the digits between the tenths need to stay the same, the hundredths need to stay the same, thousandths need to stay the same, and then the 10,000ths needs to stay the same. So let's analyze what we've got here for eccentric anomaly final and eccentric anomaly final step 2, or try number 2. 4 stayed the same, 3 stayed the same, but we jumped up from 5 to 6. So, okay, we haven't hit our convergence criteria yet. 8 and 4 stayed the same, but we don't care about those yet because we can't even get the hundredths to stop changing yet. All right, one crisis at a time. Let's do our third try. I will label that as E sub final 3. So it's still going to be mean anomaly final. Hopefully you start noticing the pattern. Eccentricity, sine of what we got for the previous iteration, 4.3684. Notice I am carrying 4 digits after the decimal. Okay. 4.5559 plus 0.2. Sine of what we got from 4.684. What's that going to give us? Oh. So it gives us 4.37, sorry, 3713. All right, well, let's do our convergence kind of check here. Let's try and write legibly. Always my challenge. 3713. All right, so 4 stayed the same from before. 3 stayed the same, but again, this hundredths digit continues to change. So, fourth try. Now, those of you who are calculator wizards might notice that there's some efficiencies you can do here. You don't have to keep writing this all the way out. And in fact, especially on a GR, I would encourage you not to. If you can do like answer plus 0.2 sine answer, or like, sorry, 4.5596 plus 0.2 sine answer from before, that's generally how you want to speed this up. So I'm going to trust that you know that M sub final is as it was before. You know what? Heck, I'll just write it out. 4.55596 plus 0.2 sine of we got from a 4.3713. Okay. Ah, darn. This gives us 4.3674. This is interesting because it popped up and then went back down. So 4.3713. Okay, great. 4.3674. Okay. Yep, looks like that hundredths digit changed again. Back to the drawing board. highlight something to you guys. Just because it won't converge on the first few tries doesn't mean you're doing something wrong. It means you're actually doing something right. And it's just part of the process. First victory. So finally down here on the fifth try, I get 377. So 4 stayed the same, 3 stayed the same, 6 stayed the same. Finally, even now the thousandth stayed the same, 7. Okay, we're almost to our convergence criteria of this 10,000th place not changing. I suspect we only have a couple more tries at the most. Okay, 6th try. Point 55596 plus 0.2 sine of what we got from before, 3677. Finally, I get 4.3677. 4 stopped changing, 3 stopped changing or stayed the same, 3 stayed the same, 6 stayed the same, 7 stayed the same, 7 stayed the same. Finally, our 0.0001 convergence criteria is met. And I'm just going to underline it because I'm so proud. All right, so our eccentric anomaly final is what we got after the 6th try. Just happened to be when it finally stopped changing. And that's 4.3677. Now, let's think about our half-plane check. Mean anomaly final. Way back in the previous sheet of paper, we found mean anomaly final was 4.55596. We've been using it the whole time. That is between pi, which is 3.14, and 2 pi, which is about 6.28. That means that its brothers, eccentric anomaly final and true anomaly final, have got to also be in this bottom quadrant here, or not wrong word, bottom half plane. Is it? Half plane check. Is eccentric anomaly final of 4.3677 between pi and 2 pi? Yes, it is. So we are good to go. Because pi, which is 3.14, is less than what we got for eccentric anomaly final, which is between 2 pi. That's the half plane check. Okay. Whew. The hard part's over. We just have one more plug and chug to do. No iteration. And I guess I would label this as maybe our 4th step here, if you want to call it that. Just finally using our highly iterated eccentric anomaly final that we really worked hard for. We're going to use it over here to get our true anomaly final. So pulling right off the equation sheet, cosine of true anomaly is equal to cosine of eccentric anomaly minus eccentricity over 1 minus eccentricity times the cosine of eccentric anomaly. Let's plug it in. So I'm going to just isolate true anomaly final is the inverse cosine of all this. So cosine of eccentric anomaly final, which we finally decided was 4.3677 minus 0.2. Be careful with your math here that you don't take the cosine of 4 minus 0.2. Make sure you say cosine of 4.3677, that quantity minus 0.2. That's a common error. All right. Let's finally get this plugged and chugged. Haha. Oh, brother. So we get 2.0988 radians. Half plane check. I have a creeping suspicion. Let's check. Half plane check. So let's see. Both mean anomaly final, eccentric anomaly final are between pi and 2 pi. What about mean anomaly final? Mean anomaly final, unfortunately, is between 0 and pi. Pi is 3.14. Our mean anomaly final and eccentric anomaly final, are between pi and 2 pi. Well, shoot. So that means what we got to do is take and do the half plane check execution here, which is to say we're going to take 2 pi minus what we got for true anomaly final. And that will finally be our answer. Whew. 4.18. 4 radians. That's our true anomaly final. And let's think through this real quick. So way back when, we were given a true anomaly initial, right? So we're at perigee. Same semi-major axis eccentricity as before. Where will it be in 12 hours? So it's asking where will it be. That means true anomaly final is what they want. And then they pitch you, they softball you a time of flight. We use a similar process to the previous problem. Start off with true anomaly initial, march that all the way forward to mean anomaly initial. We use that in time of flight, that and time of flight to come down here and get mean anomaly final. Then comes the big step 3 of going from mean anomaly final to eccentric anomaly final. That was this whole thing with the iteration. And we have to do our convergence criteria and make sure each answer starts getting closer. You want it to. Of course, we want to do our half plane check at the end to make sure that our half plane of eccentric anomaly final after the iteration is in the same half plane as mean anomaly final. Turned out it was. We used that to finally get true anomaly final, and that spat out something in the wrong half plane. We did our half plane check, and then we did 2 pi minus it to get our final true anomaly in radians. Now, the problem said that was fine, right? It didn't say you had to convert back to degrees. Can if you want to, but this is where we can legitimately stop. Whew. All right, thanks for following along, guys. You hung in there, and I recommend doing some practice with this. And don't forget your trick. Don't forget that if true anomaly is 0, it's going to chain its brother's eccentric anomaly and mean anomaly to be 0. Same for if it's pi. So we proved that in this problem, but you don't have to prove it to yourself if you buy it. I was doing that as a teaching process. So look for that trick. Look for the trick, and you can save yourself some time. Okay, thanks.